Alright, so this is part 2 of the normal distribution, section 5.1. My first question for you guys is, how many different normal distributions are out there? And if you answered or thought about this symbol, infinity, you're right. You pick any mean and any standard deviation, and we're going to have a potential normally distributed variable, alright? And lots and lots and lots of variables out there are normally distributed. Really, so many different naturally occurring phenomena in the world are normally distributed. Body temperatures of rats, 40-yard dash times, IQs, all right, those sorts of things are normally distributed. All right, so we're going to have a lot of application problems in this section where you're going to be given a mean and a standard deviation. All right, but we're not going to be able to use them in the form that they're provided to us. What we're going to have to do is convert to a z-score, which is a tool we've used before, introduced it in the previous section, and now we're gonna use it, take it a step further here. We're gonna see that z equals x minus mu divided by the standard deviation. So some particular x value you're gonna have to standardize, and it'll give you a z-score, and then you can find the area under the curve. All right. So what we're gonna see is that in this section, really so often the rest of the course, you're going to be given, let's say, mu equals 11.4 and a standard deviation of 5. And maybe we're talking about feet. Mu equals 100 and a standard deviation equals 15. IQ. Mu equals 8 and standard deviation 0.03. Maybe ounces in a Starbucks cup of coffee. All right. Whatever our situation, whatever mean we have, whatever standard deviation we have, we're going to convert to the universal translator. And that universal translator is the z-score. That's what we're going to do, is convert everything from x to z. Alright, so our example here, why don't we go ahead and use IQ as our example. The average IQ, according to this IQ metrics, IQ test, is 100 with a standard deviation of 15. Alright, now you might be saying, that's discrete data, and you might be right, I'm not exactly sure. I believe IQ is a measure of your age on planet Earth to how old you are in your brain, something like that. So age is continuous, but whatever your IQ is, it typically comes in this form, a whole number, right? 84, 125, etc. All right, so even if we have discrete data, it can behave and be modeled using a normal distribution. All right, so we certainly can do that as well. It's important to distinguish between continuous random variables and discrete random variables, all right? Discrete random variables, we saw specifically the binomial, we saw specifically the Poisson. With normally distributed random variables, they can either be continuous or they can be discrete, the data themselves. In either case, though, we model it using a smooth curve on the coordinate plane. All right, so here's what we're going to do with our z-scores. Let's draw our normal curve. And we're talking about IQs here. So we'll say the average IQ is 100 with a standard deviation of 15. So move up one standard deviation, move up one standard deviation, move up one standard deviation. Not my best normal curve here. Alright, and move to the left, one standard deviation. Let's move another one. Let's move another one. Here we have x values. Alright, our random variable x represents the IQ of somebody. X equals IQ. With each one of these x values, any x value we pick, there is a z-score that's associated with it. And in fact, we've seen the following z-score several times: 0, 1, 2, 3, negative 1, negative 2, and negative 3. These z-scores are each associated with a corresponding x value. If somebody has an IQ of 115, their z-score is 1. All right, maybe 115 is more like the average IQ of a UCF student, okay? But in this case, we'll go with 100 as our mean. All right, we'll stick with that. 100 is our mean. Sigma is 15, all right? But if your z-score is +1, your IQ is 115. If your z-score is 145, excuse me, if your z-score is 3, your x value is 145. That's your IQ. What we're doing is, as we'll see, we're just going to convert whatever situation it is into a z-score, because we're going to translate into the universal language in statistics and science standard deviations above or below the mean. That way we can use our table, our standard normal table. All right, so the standard normal is what we see right here. The standard normal has a mean of 0 and a standard deviation of 1. If we have mu equals 0 and sigma of 1, then we're dealing with the standard normal curve or standard normal table for us. So right in the middle we have 0, 1, 2, and then 3. To the left we have -1, -2, -3. This is the standard normal curve. And what we're going to do to solve problems in this chapter is convert our information, our data, our situation into a normal curve, a standard normal curve. And by the way, remember the Monty Hall problem from lab? That was originally, the situation was originally brought up in Parade magazine. There was a columnist, her name was Marilyn Vos Savant. She's in her late 60s now. This was in the early 90s, and somebody wrote in about the Monty Hall problem and said, is it better to switch or to stay? Web courses, I post a little bit more information about it, but she's the one that originally said you should switch, and here's why. And she got a lot of hate mail. The haters came out. One from the University of Florida said you blew it. You blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There is enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more. Shame. Scott Smith, PhD, University of Florida. Scott Smith, you got served, because Scott Smith is wrong, as we saw in the lab. Computer simulations show that switching is the best option. So what do we learn here? You should always listen to the woman. Always listen to the woman with the world's highest IQ, recorded IQ. Her IQ is 228. All right. So what we're going to do in our situation here is we could figure out actually what the z-score is of her IQ. All right. We're going to be able to transform from x to z using this magic formula, the translation formula right here. We're going to plug in some x value they give to us, plug in some mu, and then divide by some sigma. All right. Now before we get to do that, learn about the magic of this formula and getting z-scores and all that, we have to learn how to use our table. So let's do that with a few examples here. All right. So the table is it's table 4 in your table packet. All right. In the text, it's the appendix, page 16. All right. You basically have negative z-scores on one page, and they go from -3.49 all the way up to what's listed there as -0.00. And then on the other page, you have 0.00 all the way up to +3.49. So we could draw a picture to represent this. Another curve here. Your table lists from -3.49 up to +3.49. Anytime you look up a value on the table, it's giving you, anytime you look up a z-score on the table, let's say we looked up this z-score, 3.49. So flip your table to look for 3.49. The far left column represents the first decimal. The left column gives you your first decimal. And the top row gives you your second decimal. So basically we're going to round all z-scores to 2 decimal places in this chapter. Now if you look up 3.49, you'll see, so you look on the table for 3.49, you'll see a 4-digit probability there, and that's 0.99998. What your table gives you is every time you look up a z-score, it tells you the area to the left of that z-score. So this area your table is estimating to be right there, 99.98% of the curve. That's what it thinks it is. And that is correct. Not a lot of area to the right of positive 3.49. In fact, it's just about 0. A little tiny bit, right? By the rule of complements, about 2 in 10,000. All right? Now let's look at some examples here. How about let's do, for example 1, let's look at the area to the left. Area to the left of z equals 1.23. So how much area in the curve, the normal curve, is to the left of a z-score of 1.23? So to figure this out, we'll draw the picture. It's useful to label 0 and then label your z-score as well that's in question. I draw a large vertical line representing my cutoff point, and I want the area to the left. So really what I want is the probability that the random variable z is less than positive 1.23. Now we don't make a big deal in this section about the difference between less than negative 1.23 and less than or equal to negative 1.23. By the nature of continuous probability distributions, we're looking for area. So it doesn't matter whether or not we're talking about including the endpoint or not including the endpoint or not including the endpoint. It's not it should be positive. It's not relevant. It's not relevant. And I'll talk more about that later, all right? But here, let's just shade the area we want. We want all of this. So we're going to go to our table. This is what I like to call the table direct. All right, we want the probability that z is less than positive 1.23, Danny. And that's just right off the table. Go to your table. The column you want is 1.2. So you want to go down to 1.2, and you want to move over to 0.03. And the number you see right in there is our answer, which is 0.8907. So how much area is to the left of a z-score of 1.23? The answer is about 89% of the curve is to the left of 1.23. So what's the probability that we have a random variable that's less than positive 1.23? The answer is 0.8907. All right, let's look at number 2. How about the area to the right of, how about 0.93? Draw our picture. Find 0.93. There's 0.93. We want to figure out what this area is. Now our table gives us the area to the left of a z-score, but we want the area to the right here. So there's 2 ways we can approach this. The first way is to just use complements. We know that the total area under the curve is 100%. This is all 100% in there. So if we call maybe the area we want, we'll call that A. And we'll call everything else area B. A plus B equals 1. We don't know area A, we want area A. If we could read A directly off the table, that would be great. But our table only tells us the area to the left of a z-score. So we can figure out what B is. So if we figure out what B is, we've got A. So let's just solve this right here for A. A equals 1 minus B. So area A equals 1 minus, and we can just look up 0.93 on the table, and we get 0.8238. So our answer is 1762. And notice both of these probabilities, areas, add up to be 1. So that's one way we can do it. We can use complements. And here's the general rule for area to the right. If you want to do it this way, it's 1 minus your table value. And that's area to the right, or area that's greater than, right? In this problem, we're looking at the probability that z is greater than 0.93, right? The numbers on the number line that are greater than 0.93, those are to the right, so we want area to the right. So this is one way we can do it. The other way we can do it is to use the symmetry of the curve. Use the symmetry of the normal curve. So, as originally written, the problem was find the probability that z is greater than 0.93, or area to the right. Now imagine taking this, put your hand flat on your computer screen, and then flip your hand over. So, whereas before we wanted this area, imagine flipping this curve over. Flip it. Go ahead and flip it. You have permission to flip it. If you flip it and you flipped it correctly, this is what we have now. What's the relationship between those red areas? They're the same because of the symmetry of the normal curve. They're the same. So you could flip it and then just look up negative 0.93. You get the same answer. Those are the same. They're the same because of the symmetry. So you can either use complements or just flip it over and find the area to the left. And that will be just right off the table again, okay? So this right here, let me write out maybe an overkill series of statements here, but just to make sure we're clear on this, all right? The probability that z is greater than 0.93 equals the probability that z is less than negative 0.93. Which again equals 0.8238. Okay, so we've looked at area to the right, we've looked at area to the left, those first two examples. What about area between? In between two z-scores? Those are the only situations we can deal with. How about area between? Let's say we have, I'm arbitrarily picking these z-scores, by the way, just so we get some practice here. Let's say we have this picture. All right, there's 0. How about this area? So suppose we wanted to find this probability. that z is between negative 2.76 and negative 1.13. If you look up both of these values in the table, it's going to give you the area to the left. Hey, look me up in the table, area to the left. Hey, look me up in the table, area to the left. If you know this distance or this area and you know this area, what's the area between them? It's the subtraction of them. So for this one, I say it's table minus table. Which value do you look up first? Doesn't matter. Just know that you can't have a negative probability, so you're always taking the absolute value. But to ensure you get a positive, you want to look up the one that's going to lead to the bigger area, and that will be the negative 1.13 in this case. But again, it doesn't matter as long as you have your probability wits about you. All right? So what we're going to do is we'll look up the table at z equals negative 1.13 minus the table at z equals negative 2.76. All right, that's going to give us 0.1292 minus 0.0029 for a total area or probability between those two z-scores of 0.1263. To recap here, we first looked at finding area to the left of a particular z-score. Alright, so we found area to the left of z equals 1.23. We found area to the left. We saw that we just looked that directly up on the table because the table tells you area to the left. Next we looked at finding area to the right. And we saw two ways to do that. There's two ways to solve that. You can use the table right away and just 1 minus the table value. Or you can just flip your picture. Flip your picture and then look up directly the negative value or the positive depending on the situation. Alright? And then the last situation we looked at was area between. And those are the three situations you'll face here the rest of the way when dealing with the normal curve for the rest of the course, which we'll be dealing with the normal curve in and out over and over and over again. So there's really three areas you can find. To the left, to the right, and between. You cannot find with continuous random variables exact probabilities. You can't do it. Unlike in the previous chapter where, yeah, easily you could, what's the probability of 4 wives, right? Or 4 husbands for a particular individual in America. You could find that. But here we treat our probabilities as a smooth curve. And we treat our probabilities as area. Last thing here, imagine we have this this normal curve here. Put this in red because it's really important, alright? And suppose I wanted you to find the area between here and here. You'd say, okay, I can find that, and I would agree with you. You can certainly find that. But imagine that I shrank that area a little bit, and I said I want you to find the area between here and here. Say, okay, I can find that. But imagine that I said to you, find this area. You can't find the area of a line. It doesn't have area. We'd say the probability there is 0. And we'll talk more about this in class.